Hello, hello. So here we are, trying to give a brief introduction to the metric system and dimensional analysis. And yes, you're in an anatomy and physiology class, and we need to talk about math. So let's do this. What is the metric system? Well, the metric system is basically units. I don't know how to explain it any better than that. It has to do with units. Units are really important in science and in medicine, period. How to put this? If somebody were to say, I am 5, what does that mean? Does it mean they're 5 feet tall? Does it mean they're 5 years old? There could be a number of things that the number 5 can mean. And the same thing goes in science. You can't just say, the blood pressure is 120. That's not really relevant. But if you said that's 120 millimeters of mercury, now we throw some units at it, and those units are how we're going to be applying the metric system and how we're going to be applying dimensional analysis. And then, in pharmacology, you guys are going to be doing conversions and all that sort of stuff. So this is how we do it, is by using the metric system. So the metric system itself is this, where the system and where we take the basic units for length, mass, time, temperature, and volume. Right here in the United States, length is inches and feet, and sometimes we use yards, and sometimes we use meters and miles, and it's all over the dang place. But in the metric system, it's always going to be related to a kilo. Sorry, not a kilo. A meter. I just read kilo down below, so I said it. It's funny how the brain works that way. Mass in the metric system is always grams, right? In the United States, mass could be anything from ounces to pounds to stones. I mean, there's all sorts of weird things that we do. But in the metric system, it's always the same thing. It's grams. Time is the same no matter what, seconds and minutes, so forth, so on. Temperature in the metric system is in Celsius, and then volume is always in liters. Now we can abbreviate a prefix onto these things and change the number value that goes along with it. And that's what's down below, the metric prefixes: kilo, deci, centi, milli, micro, nano. There's a lot of other ones, and we're going to see a table of what's going on in just a minute. As you guys are going through and learning the metric system, you are definitely going to need to be able to convert between different quantities within the metric system itself. So say, for instance, how many centimeters is 1 meter? So they're both length within the same metric system. They're both length, and you'll have to convert meters to centimeters or centimeters to meters or millimeters. You get the point. But you'll also have to be able to learn to convert the metric system to English units and vice versa, English units to the metric system. We're going to be using something called dimensional analysis to complete that. Crazy, crazy foundation topic. You're going to be using dimensional analysis throughout AMP1, in AMP2, in nursing program, in sonography, and wherever you're at, okay? This is going to be important for everywhere. So as you're studying this, you got to have that calculator and scratch paper and just keep going. Metric system is used everywhere in the world, and that's why we here in the United States need to know it. There are only 2 other locations besides the United States that don't use the metric system, and that is Liberia, because the United States, quote unquote, liberated Liberia, and therefore they use the same system as us. And then Myanmar, I don't know why they don't use the metric system, but there you go. So we got to be able to communicate with the rest of the world. Metric system it is. We use the English system because, we're English. But I just want to make sure that you guys know that it doesn't really matter whether we're here in the United States or not. A lot of the businesses, not just in the medical world, but also in engineering and all that sort of stuff. You can see down below food, technology, vehicles, time. Well, they're all working off of the metric system as well. Pretty straightforward. A metric system is used in medicine. So you go to the doctor's office, you weigh yourself in pounds. Well, the doctors are going to put all that in kilograms. They're not going to be putting it in pounds. So that's just the reality of it. And then anytime you're doing any pharmacy, pharmacology, drug dosing, it's all going to be in the metric system as well. So yeah, it's important. All of our blood values, all that sort of stuff. All right, so the commonly used units of the metric system. Now we're really starting to get into taking some notes. For length, we got meters, and we want to write this down. Even though it's right there in front of you, you want to take this right here, and you want to make sure that you're writing each one of these things down. So length, make sure you understand that length is always recorded in meters. Oh no, my black marker's going out. And meters is abbreviated with a lowercase m. Volume is always recorded in liters. And liters is always an L. I almost always use a capital L, but you will see a lowercase l from time to time, but that can be confusing. So I recommend always using a capital L. Mass is always in grams, which is just a lowercase g. Temp is in Celsius. We'll come back to that. Time is always in seconds, and when we can do conversions from seconds into minutes and so forth, so on. But the main three ones that you guys are going to be using throughout AMP1 and AMP2 are here: meters, liters, and grams. And then there's going to be some other things that you're going to start learning about, like millimeters of mercury and what else? Milliequivalents and that sort of stuff. So the deal is if you can learn this, then it'll work with any other units that we end up covering in the medical field at all. Just to give you some base equivalents for each one of these things, like 1 gram is 1 paperclip, so it's pretty darn light. And then 1 meter is basically a yardstick, a little bit longer than a yardstick. 1 liter, a little bit more than a quart. And then you guys somewhat understand the whole Fahrenheit Celsius thing, I think already, but you know, freezing 32 degrees Fahrenheit is 0 degrees Celsius. And then 98.6, which is your body temperature, that's 37 degrees Celsius. So 37 degrees Celsius is a pretty important number and unit for you guys to know, just because that's relevant to medicine. Now, when we really want to get down to the nitty-gritty, we're not going to always use just meters, not just liters, and not just grams. We're going to be able to give a reference point to how many meters there are by using a prefix like micro, kilo, milli, nano, and there's quite a few other ones of them as well. So whatever the prefix is, say for instance micro, then we're just going to put a symbol for micro in front of the meter. So you can see that on the screen here. So micro, the prefix micro is abbreviated with this Greek letter mu. We don't use an M because milli has the abbreviation of M right here. So a micrometer is going to be this mu M. So that's micrometer. Kilo is always a K, so that's nice. Milli is always an M. Nano is always an N. Centi, when we get there, starts with a C, so that abbreviation is always a C. The only tricky one is this micro, in my opinion. Micro you can also write out as MC. Sometimes you'll see that. Here's one on Celsius. Freezing 0, 10 degrees Celsius, 50 degrees, 20 degrees Celsius, 68 degrees, 30 degrees Celsius, 86 degrees, and 40 degrees Celsius is pretty darn hot. I don't know if you saw, the heat wave in Europe right now. There's been over 40 degrees Celsius, and that's hot for them. 37 degrees is the one that I mentioned. That's 98.6 degrees. So that one's pretty relevant to you. But you can see that Celsius, we just go 0, 10, 20, 30, 40. Often we just do multiples of 10. And that's kind of what we go on here. This is all about multiples of 10 or factors of 10. And I'm going to go into what each one of these things means. But for example, a kilometer is 1,000 times a meter. Kilo is 1,000. We're going to be going through and learning what all the prefixes actually mean using a table. It's a lot easier. But man, in science, we end up having a lot of situations where things are really, really small. So for instance, the concentration of potassium in your bloodstream, it's really small relative to everything else. But we don't want to be saying, hey, we got 0.000000075 grams of something. That'd just be ridiculous. So instead, we're going to use a prefix of nano, and you guys will see what nano is. It's basically 1 times 10 to the minus 9 for anybody that knows what that means yet. But yeah, that's how we'd end up writing it out, is 75 nanograms, because that's a lot easier than saying 0.000000075 grams. This is just a little, hey, you're going to go to the bank and get 10,000 pennies? Probably not. So here is the table that you can look at. You don't need to know everything on here, okay? We'll definitely minimize how much you have to learn off of this. But this is the general prefix table all the way up to 10 to the 18th power. I mean, that's a big number. Giga is a billion. 10 to the 18 is quintillion, whatever the hell that is, right? 10 to the 15 is quadrillion. So exa and peta and tera. So you might recognize tera because of terabytes, right? They use these prefixes when it comes to computers and computer memory, gigabytes, megabytes. These are big numbers. And I'm sure they're hoping to get peta. They might already have it and I don't even know it. But yeah, we don't deal with these numbers in biology. That wouldn't make too much sense. Mega, we don't deal with mega in biology. That's a big number. Millions of anything is typically too big in the human body. Kilo. Now here's one that we do use, like kilogram. Kilo. And the meaning is 1,000. That's 1,000. All right, and what that means is it's 1,000 of the base unit. I'll explain what that base unit is. I'll write this all out. I might as well start doing that now. But in essence, if we have a base unit of a gram, this is the base unit. Base unit, we just say it's a G, but what that G really means is that it's 1. Does that make sense? 1 we can kind of just ignore, or we could add. And when you just write the base unit, it's normally just the unit, gram. But what that really means is that there's 1 gram of it available. So now what we do is we say things like deca, hecto, kilo, 10. So this is 10 to the 1. That's the multiplier. And what that means is we just start adding zeros. So if I come over here and I take 1 gram, 1, and I add a 0 to it, now I'm at 10. Does that make sense? So if I had 10 grams, what would that 10 grams actually be? Well, it's either 10 grams, or you can say that it's 1 decagram. You guys are not going to use deca. I'm just trying to use this as an example. All we do is add this 10 to the 1. If I add a 10 to 1, now I'm left with 10, versus hecto, 10 to the 2. So if I take that 1 of my base unit and I add 2 zeros, 1, 2, now I have 100 grams, which is what it says. This is 100 grams. 100 grams is equal to 1 hectogram. Now let's get to that kilo, right? Kilo is 10 to the 3. So what does that tell us? We take 1, we add 3 zeros. So there's 1,000 grams in every 1 kilogram. That's how we go about doing this. To go to the bottom side of this table, units can be smaller than a gram. And we go all the way down to pico and even femto when it comes to science in a laboratory. But picograms are relevant to something that's in your bloodstream, and that's 1/1 trillionth of a particle. It's very small. We're more likely to use micros and nanos, but we do sometimes measure things in the pico level. So what we do is we say we still have our base unit, which our base unit is 1, and we're going to go and continue with the whole 1 gram idea. This is base unit. Oh, I already wrote that over there. Whatever. Lo siento. So here we are, and we say, let's go with deci. Well, deci is 1 times 10 to the minus 1. Now, for those that don't remember, you just start with your 1. Now, instead of adding a 0 here, we add a 0 here, and we move a decimal place over. Okay, so we just move that decimal place 1 point. So now I'm at 1/10 of something. So 1/10 of a gram. And 1/10 of a gram is equal to 1 decigram. Let's do it with centi. Centi is 1/100th. So 1/100th, now I take my 1, and now I'd move a decimal place 1 spot, 2 spots. I'd add a 0 there, I'd add a 0 there. So now I have 0.01. I know that might not look right. We'll go ahead and write that out, 0.01. But that's 0.01 grams. So 0.01 grams is equal to 1 centigram. Milli, you're going to be using milli a lot, and this will be my last example here, but milli is 1/1000th. So again, we just take our 1, we take our decimal places, we move them out, 1, 2, 3, we put our decimal place here, so 0.001 grams is equal to 1 milligram. So I'm hoping this somewhat makes sense, and we're going to use this in dimensional analysis to help us figure things out. But that's in essence what we do with the prefixes. So anytime you're thinking of a milligram, what you need to say is how many milligrams are in a gram, or you can go how many grams are in a milligram. Often I like to say how many milligrams are in a gram. So I'd have to think about this the other way around. So if I had 1 gram, well, now I take and move this decimal place 1, 2, 3 to get to 1 gram. So I'd have to take and move this decimal place 1, 2, 3. So 1 gram is equal to 1,000 milligrams. So that's the better way when we're doing the math. This is going to be a really nice way to be able to think about and do our conversions. But you can see that right here. Milli is 1,000th. So how many milligrams in 1 gram? Well, it's 1,000 milligrams in 1 gram. So another way to think about milli is like millennium, right? How many years are in a millennium? 1,000 years. How many years are in a century? 100 years. If I move something a decimal place, decimal, 1 decimal place is 1/10. So the words exist in real life, and we can pull out, some word that makes sense to us, decimal place, centipede, millipede, century, millennium, and we can make that make sense for us as we're trying to memorize these, because yes, you need to memorize those. So the ones you guys are going to need to know: kilo, the base unit, of course, deci, centi, milli, micro. And I think I never go to nano for y'all, so you should be fine. But The commonly used ones: kilo, deci, centi, millo, micro, and then nano, of course, in the medical field. But I probably won't make you guys go down to the nano level. So what I'd like for you guys to do is I want you to stop and I want you guys to think about how this would all work out. So if I had a kilo, what is the fraction or the multiple that's used? So we just did that over here. So 1 kilo, what is the fraction that would be used here? So if we go back to our table, right, that's what we're talking about. What is the fraction that's used? 1,000. Or the multiplier, which is listed over here, is 10 to the 3. So we'd say 1,000 or 10 to the 3. Deci, 1/110th or 10 to the minus 1. Centi, 1/100th. Milli, 1/1000th, and so forth, so on. So what I recommend that you guys do is pause the video and fill this out on your own. But we're going to be moving on, and I'm going to show it in the next slide. So yeah, please, I'll give you a chance to pause. 1, 2, 3, and then moving on. So here it all is, exactly as we started out, 1,000 or 10 to the 3, so forth, so on. You need to be able to convert between metric prefixes. We're going to be doing this all the time. So for instance, you're not going to take something and measure it as 100,000 grams. We're going to want to get it down to the most reasonable unit that we can try to calculate something in. So 100,000 grams, well, that's actually 100 kilograms. So how can we go about doing that? There are a couple different methods. Something that you may have learned in the past is called the number line method. I don't recommend the number line method anymore because things are going to start getting too complicated to use the number line method. If you do have a problem that you can convert inside the metric system, then you can use the number line method, but I'm not going to reteach it to you. If that's something you already know, great. If not, the more reliable method is called dimensional analysis. And so what dimensional analysis does is it's going, and I'm just going to do one real quick without explaining it, but it's going to allow us to say if we have 100,000 grams, that's not an extra zero. If we have 100,000 grams, how many kilograms is this? So I'm going to take and say, how many kilograms is this? And in order to do dimensional analysis, we're going to have to get rid of the gram, and we're going to have to convert it, dimensional conversion, dimensional analysis, we're going to have to convert it to kilograms. So I'm going to just show you real quick how I do it. I'm not going to say too much. Okay, I have to get rid of grams. So in order to get rid of anything, A times 1 over A equals, well, that's just A over A, which actually just equals 1, right? We can cross cancel those out. So if I have grams on top here, how can I get rid of grams? I'm going to put grams down on the bottom here. I'll explain this a little bit better too, and I'll explain it even in class as well. But now as I add those grams in, I can get rid of those units. And I have kilograms on top because I know I want my final units to become kilograms. So now I have kilograms over grams. And now we use this list of things over here and we say how many kilograms are in a gram, or even easier, how many grams are in a kilogram. So what do we know? We know that there are 1,000 grams in 1 kilogram. So we say there are 1,000 grams in 1 kilogram. And what I've done here is I've made it so the top of this new thing, this is all brand new. I invented this. I put this in myself. But I made it so that the numerator on top is equal to 1 kilogram. But look at what the denominator is also equal to. What is 1,000 grams equal to? 1 kilogram. So now the top is 1 kilogram and the bottom is 1 kilogram. The bottom just has a unit that I can get out of here. So now I have grams that are cross-canceled out, and I'm left with kilograms, and it's just 100,000 divided by 1,000. Well, what's 100,000 divided by 1,000? Just get rid of 3 zeros, and we're left with 100 kilograms. And do you guys see how that is what the answer was supposed to be? Instead of 100,000 grams, we now have 100 kilograms. They're the same thing. 100,000 grams is equal to 100 kilograms. That's called dimensional analysis. The number line system uses this whole King Henry died unusually drinking chocolate milk. It's doing the exact same thing. If we would have had 100,000 grams, then we would have just moved things over and we would have said there's 1,000 of the base unit in it, and we'd be able to move just decimal places. Not too hard to do, but in big conversion problems, dosage problems, pharmacology, nursing, you're not going to be able to do that. You're going to have to use dimensional analysis. And dimensional analysis is really powerful because it allows us to convert easily between all units, not just within the metric system, but between the English system and the metric system. And that's exactly what all these terms say. We're converting things. We're creating a conversion factor that allows us to change the unit. And when we change the unit, the units all are going to have the same dimensions of the original unit, which is cool, which is what we're after. It's all about making numerators and denominators. And I hope you guys remember that from basic math, right? And like terms can be canceled out. Like terms are just like terms. As I wrote out here, this is just something that maybe once upon a time you guys learned, and it's not too complicated to think about. A times 1 is A divided by A. And what if I did A times B over A? Well, again, I get a cross cancel, and that's just going to equal B. What if I did something like A times B divided by A times C divided by B? These are the same things as using units. What if this was grams, grams, kilograms, kilograms, and the final thing was something else? Well, A are going to cross cancel, B are going to cross cancel, and we're going to end up with something else. That's the whole like terms can be canceled out. The like terms, these are units. It's pretty cool. I don't know why this isn't working. 1 second. Why did all of a sudden decide not to work here? 1 second. There we go. All right. The conversion factor basically must equal 1. It's an equivalency. It's equivalent in the form of a fraction. So there's a lot of weird words in here, but in essence, this just says the conversion factor, you can't just invent something crazy and weird. One quantity has to be equal to the other quantity. Exactly as I explained up here. 1,000 grams and 1 kilograms are the same thing. It gets more complicated when we're trying to convert between the metric system and the English subunits. So for instance, how many milliliters are in a quart? They're 2 completely different units. So how do we make that all work? Well, we can actually go online, go in our textbook, and we can see how many milliliters are in a quart. So if I then gave you, hey, we got 5 quarts, how many milliliters are there? You can use dimensional analysis to say, I have these many milliliters in these many quarts. An example, Amy is donating blood today. The Red Cross accepts 1 pint of blood per person per visit, then rewards you with juice and a sweet snack. Yum, yum. There are 2 pints in 1 quart, 1.06 quarts in 1 liter, and 10 deciliters in 1 liter. How many deciliters will she be donating? Yep, it gets a little crazy. And I'm not trying to freak you guys out with this. We're not going to be doing anything this complicated to start off with in our lab reports or anything like that. But I'm just trying to get you guys to see that really all we have to do is start to line up those units. She is donating 1 pint, right? Accepts 1 pint of blood per person. So what do we know she starts with? She's starting with 1 pint. What do we know that we want to, what are we asking, I guess I should say? How many deciliters will she be donating? So in the end, we need to convert all this to deciliters. And that's how I go about this. So 1 pint, I need to get it over to deciliters. But what do we know? We know 2 pints in a quart, we know 1.06 quarts in a liter, and we know there's 10 deciliters in 1 liter. Okay, well, deciliters. I almost work my way backwards here. There's a couple different ways to work your way through this, but we know deciliters needs to be our final units. I know that. So over here, I know I need to have deciliters as my final unit as a numerator. Because remember, deciliters, technically this is just deciliters over 1. So deciliters is numerator and the 1 is a denominator. So I know I need deciliters at the top. That's how I think through this. Well, now I go back to my problem. Well, what do I know? Well, I know there's 10 deciliters in 1 liter. So there's 10 deciliters in 1 liter. I am not writing down any numbers yet. I am only writing down units. This helps me line everything up the way it's supposed to be. So that's what I need. I need deciliters, and I know how many deciliters are in a liter. So let's work our way backward through our problem. Now I know I need to get rid of liters. I can't have liters in my final answer because this is deciliters over 1, not deciliters over liter. So what do I need to do to this liter? I need to get rid of it. And in order to get rid of it, I'm going to have to cross cancel it. So liters and liters now cross cancel. This is all set up. Well, we go back to our problem. We say that there's 1.06 quarts in 1 liter. So if I have liter here, now down here, I can put quarts because I'm going to know that there's 1.06 quarts in 1 liter. But I'm just not adding numbers yet. I want to line up my units. If you can line up your units, then you're doing it right. Let's go one step back. How many pints quarts? Well, quarts. Is quarts a denominator in our final solution? No, I just want deciliter by itself. So what do I know I need to do to quarts? I'm going to need to get rid of it. So in order to get rid of quarts on a bottom, I'm going to have to cross cancel it with quarts on the top. And now I can say there are 2 pints in a quart. So now I'm going to have pints down here. Now this pint is going to cross cancel with this pint. So let's walk our way through how we just did this so you can see that the units all line up now. Pints cross cancels with pints. Quarts cross cancels with quarts. Liters cross cancels with liters, and what units are left over? Only deciliters. And that's the final answer that we wanted. This is a very complicated problem that we just worked our way through. Now we can add the numbers. She started with 1 pint. Well, there are 2 pints in 1 quart. There are 1.06 quarts in 1 liter, and there are 10 deciliters in 1 liter. And now we just do the math. 1 times 1 times 1 times 10, 2 times 1.06. So now this is 10 divided by 2 times 1.06. And then you'll get your answer. I don't know, 4 point something. You guys will need to practice this. This is a very complicated problem, though. You're not going to have anything that's this complicated. Promise you that. Okay, this is just hey, this is how we line this up in lots of different ways, but ultimately it's about lining up the units so that the units start where you have. This is what you have. This is the only thing you really have, and this is what we want to finish things with. Ask yourself, what is the question? What are you asking? Well, this is what we have. What is the equivalency? Well, the equivalency, those were all given in the question. That's 1 quart, 2 pints in a quart, 1.06 quarts in a liter, so forth, so on. And then you convert those by lining them up so that they can cross cancel. And then you just cross cancel those terms, and then you do your final math. As long as when you cross cancel, your final units match what you ended up with in your problem, then the numbers will be correct. I love that about dimensional analysis. As long as everything that you've done here got you to your final units, then everything else will be correct. The last little bit that you guys will need to do for this lab report is know how to do scientific notation. And scientific notation is all about just moving decimal places. So for instance, if I gave you the number 1500 and I said convert this to scientific notation, it's all about factors of 10, powers of 10. So you just take and put a decimal place in the basically between the first whole number and the second whole number, always there. So here, I'd put a decimal place right here. So it'd be 1.5. And then I'd ask myself, how many decimal places did I have to move to get there? 1.5, I would have had to move this decimal place 1, 2, 3 times to the left. So this is 1.5 times 10 to the 3. Over here on the second problem, I give you this smaller number, 0.00056, and I say convert to a scientific notation. So now I put the decimal place between the first and the second whole number, 5.6. And then how many times did I have to move the decimal place to get there? 1, 2, 3, 4 to the right. So now I just say it's 10 to the 4, but it's 10 to the minus 4 because I moved it to the right. If you move the decimal place to the left, we're getting bigger. If we move the decimal place to the right, we're getting smaller. Always put that decimal place after the first non-zero digit, your first whole number. Just put it there and then count. Count the number of spaces. That's always going to be going. If it's to the right, then it's a negative. If it's to the left, then it's a positive. All this is written down here for you as well. So when you get the free time, go ahead and convert these to scientific notation. Press pause, get her done. 1, 2, 3, and there we go. We take our 3.6, we say how many decimal places do we move? 1, 2, 3, 4, 5, 6, 7. We went to the left, it got bigger, 3.6 times 10 to the 7. Over here, we put that decimal place after the first whole number, 5.23. How many decimal places do we have to move? 1, 2, 3, 4, 5. We went to the right, so it's minus 5. And that's how we do scientific notation. Make sure for the exam that you guys can walk through common units for the metric system, know how to combine those units with the prefixes like kilogram or, kilometer, so forth, so on. Know the fraction and the multiple for each of these prefixes. Kilo is 1,000 or 1 times 10 to the 3, so forth, so on. Be able to solve metric conversions and dimensional analysis math problems. And that's something that you guys are going to be practicing in lab. All right, that's the end of the story. And hopefully I can figure out how to stop this recording and hopefully it's helpful.